Okay, we'll go ahead and get started. So welcome everyone to the M-Cubed seminar. I'm very pleased to welcome Mingyue Tang. Mingyue is a PhD candidate at the University of Hawaii at Mānoa and has recently completed her PhD defense under the supervision of Dr. Giuseppe Torri, so congratulations on that. Her dissertation is titled Mechanistic Understanding of Tropical Convective Organization and Propagation. Last year during her visit here, she presented her work on the role of cold pools in modulating convective organization under the MJO. The work she will present today was developed during her ASP graduate visitor program visit in collaboration with Jimmy Dudia and Changhai Liu. She shared an early version of this work at the M-Cubed Happy Hour seminar last summer, and the feedback she received there helped shape what you'll see today. Welcome.
Thank you so much for introducing and also attending my seminar today online and also in person. So first I want to acknowledge my collaborators, Jimmy and Changhai from NCA, and also my PhD advisor, Professor Giuseppe Torri from University of Hawaii. So let's start with our favorite cold pools. How does a cloud form a cold pool and help organize convection? To start with a precipitating cloud. When the cloud droplet drop out of the cloud base, they will enter a very unsaturated environment and begin to evaporate quickly. This will drive very strong evaporative cooling to build a pool of cold, dense, and dry air. Because of the negative buoyancy, they will sink and spread out along the surface. So first, because of the pressure gradient at the gust front, it can lift the cumulus upward to become a new convective cells. This is also well known as RKW theory. And RKW theory mainly explains why the mid-latitude skull lines can persist for several days. It emphasizes the role of low-level wind shear and how it interacts with the cold pool to create a vorticity balance, generating strong updraft at the front. However, in some certain environments, like in the tropics, achieving such strong low-level wind shear seems hard. And besides in the tropics, we have abundant moisture, so the environment below the cloud base may not be so dry as in the mid-latitude. And then the evaporative cooling may also be weaker. But luckily, we still have a lot of moisture in the tropics, so besides of the dynamic forcing, there is another argument that cold pools can generate new convective cells by thermodynamic forcing. We also call it the moist patches theory. That means when the cold pool's extensive current is going to recover its neutral buoyancy, even a little more moisture anomaly can lead to a sudden increase of moistatic energy at the edges of cold pools. So the parcels there may have more thermal advantages to become new convective cells. Both these two ways can show that cold pools can generate new convective cells to help organize convection. And unlike the evaporative cooling-driven cold pools, the land breeze is produced by nocturnal radiative cooling from the surface. But in sense, both systems come from boundary layer cooling that create negative buoyancy, so they behave as density current that moves horizontally. When I first started studying this project, a more theory-oriented question kept coming to my mind. Can I study the land breeze in the same way we have studied cold pools before? If yes, what are their similarities and what are their differences? And what makes the tropical special compared to the mid-latitude? Do moist patches play a role in the land breeze as well? I want to raise this question first, and I hope that through the following work on convective offshore propagation, we can obtain some insight into these questions. Next, we go to this phenomenon called convective offshore propagation. It's specifically referred to a specific phenomenon in the coastal regions where the convection frequently propagates offshore during the nighttime. This is a global map showing nocturnal convective offshore propagation in the diurnal cycle. And most coastal regions around the world exhibit this propagating dynamic feature. Notably, the Maritime Continent has a very strong and very stable diurnal offshore propagation. This may be due to its unique location between the Indian and Pacific Oceans, where the sea surface temperature are very high, and a complex interplay of land, ocean, and atmosphere. Offshore propagation offers a valuable opportunity to improve our understanding and modeling of cross-scale interactions. However, the underlying mechanisms driving offshore propagation still remain open question in different regions. In this work, we focus on New Guinea Island, which has the most stable offshore propagation, and it is also the biggest island in the tropics. The animation here shows the February climatological diurnal cycle of precipitation rate and the prominent offshore propagation on both two sides of the islands. The strong rainfall bands start over the center of islands, but their coverage is more than twice the size of the island itself. This suggests that propagating organized convection has a high chance of producing an upscale effect. And second, if we look more closely, we can see that after the rain moves down along two sides of the mountain ridge, they will dissipate first and then regenerated after reaching the coastline on both two sides. This process looks like a distinct jump between two propagating rain bands over land and ocean respectively. Later, we'll refer to this as the first and second modes of convection during the convective offshore propagation. There are many factors that could be key mechanisms influencing nocturnal offshore propagation. Among this, the most widely recognized but still difficult to distinguish are density currents and gravity waves. Density currents, which are slower boundary layer dynamics, can be caused by various cooling sources. For example, radiative cooling over land at night can drive the land breeze that push the convection offshore. In the regions with mountains, katabatic winds may also contribute. And also, as shown in this animation, again, evaporative cooling-driven cold pools can trigger new convection along its edges, helping to push the system offshore as well. So in this work, we want to answer the overall question: how do multi-scale density current influence diurnal offshore propagation of convection over New Guinea? And we will specifically answer two questions in the first two chapters. The first one, what process contribute to the emergence of two distinct modes of convection and the abrupt jump between them? And second, what factors enable convection to propagate such long distances offshore, always more than 200 kilometers, and sometimes more than 600 kilometers over ocean, and persist for such an extended duration? To answer these questions, we use both observation and simulations in this study. We first used stream enriched for 21 years to study the climatology. And also we use ERA5 analysis to study the large-scale background, especially influenced by the cross-equator monsoons. We focus on the month of February, when the offshore propagation around New Guinea is the strongest, and the northerly part of the cross-equator monsoon is also the strongest. For comparison, we also look at August, when the southerly monsoon is strongest. For the WRF simulation, we follow Hasem et al. 2016 in choosing February 2010. But here, we focus on a more smaller timescale through a case study to understand the physical process in more details. We run WRF model with 2 kilometer gray spacing. Here, the domain is single but very large to cover New Guinea and also the nearby ocean. The main case is a 3-day period from 19 to 22nd February 2010, which shows a very strong offshore propagating event. We then run two kinds of sensitivity experiment. The first one is a higher SST experiment, where we uniformly added SST by 0.5 Kelvin's degree to show a slightly warmer ocean. And then we'll apply the cold pool denying experiment to turn off all the evaporative cooling. For the first question, we constructed two different kind of coordinate system to quantify different stages of offshore propagation. First, in the left panel, the colors here represent the topography height. New Guinea features a mountain ridge over 4 kilometers high, which contribute to a land-based convective initiation in diurnal cycle. We define the x-axis here along the ridgeline and set offshore direction as the positive y-axis. In the figure on the right, the Hallmark diagram has the horizontal axis represent the distance from the ridgeline, which is the y position in the left panel. And the y-axis here represents the diurnal local time unit in hours. During the diurnal cycle, the precipitation initiated around 2 p.m. near the ridgeline and then split into two branches, symmetrically moving towards the coastline. We refer to this as the first mode. After a brief disappearance of convective signals, precipitation regenerates and continues propagating offshore to even greater distances, seems also symmetrically on both two sides. It's also interesting that in the region where this convective jump occurs, we also see weak onshore propagating convection during the afternoon earlier than this jump. So what could this mean? To more accurately describe the locations of this onshore signal and the regeneration, we establish a second kind of coordinate system with the northeastern coastline as the x-axis. In the figure on the right, the horizontal axis here represents distance from the coastline. The left panel shows the climatological distribution of precipitation rate in February, which further support the idea that the local environment and the stable dynamics alone can produce these two modes separated by a dry gap. What stands out is that the second mode begins precisely over the warm ocean. And additionally, the afternoon inshore weaker convection started around 12 p.m., also exactly at the coastline. This suggests that the sea breeze persists and even strengthens in the afternoon. By advecting moisture, the sea breeze could also interact with the first mode of convection. So why does this jump occur? And what role does the sea breeze play in this process? We simplify this complex process into an interaction between two opposing motions. First, we estimate the speed of the signals. The first mode moves the fastest at over 7 meters per second. Meanwhile, the sea breeze moves significantly slower at 3.7 meters per second, but begins departing about 2 hours earlier. The next question becomes a simple math problem. Given the distance from the ridge to coast, where will they meet? And based on simple calculations, they are expected to meet about 6 hours later at about the halfway point of the distance. During this time, the sea breeze acting as a colder density current travels around 110 kilometers, which is also the distance where the cold air remains trapped in the boundary layer. This explains why the first mode of convection struggles to propagate further, leading to a jump of nearly 100 kilometers. At the same time, as a source of moisture convergence, the sea breeze intensifies and localized convection originates from the ridge when they meet. This is often where the highest precipitation rates are observed over New Guinea rather than just over the mountain ridge. Moreover, the localized convection becomes organized and can persist for 10 hours, which is nearly half of the diurnal cycle. For this organized convection, it can generate stronger cold poles that interact with the land breeze. We believe this sea breeze cold pole land breeze locked interference forms a critical physical mechanism for association between the first and second mode. We also see these important characteristics in our simulations. In the figure, the red and blue colors show the perturbation potential temperature near surface, and the streamlines shows the near surface wind with colors marking the wind speed. In the cold pool denying experiment, from 3 p.m. to 6 p.m., we can see a long-lasting onshore sea breeze. These sea breeze fronts are very clear. They mark the boundary between the warm and cooler air in the boundary layer, and they are almost perfectly parallel to both the straight and curved coastlines. As a result, the cool air becomes trapped in the boundary layer by sea breeze and stays onshore through the afternoon. This means the first mode over land cannot easily reach the near coastal ocean, which helped to explain the dry gap near the coast. So here are the key messages from this chapter. The first one is consistent with many former papers. The island rainfall exhibit a double peak. One is afternoon precipitation over land, and another one is the early morning peak offshore. Specifically in this work, we distinguish two modes of propagating convection. Clarify their different triggering mechanisms, show how they interact, and contribute to a process-level understanding of offshore propagation. And here the important part is also about the sea breeze, because the sea breeze is not just the local onshore wind, but the propagating thermal structure with weaker convection along its front. It traps the cold air from the coast inland before meeting and strengthening the propagating convection, stabilizing the boundary layer and hunting the coastward advance of the first mode, hence a long jump about 100 kilometers. And next, we use high-resolution warp simulations to explore more details about most boundary layer dynamics. In February, the cross-equator monsoon bring dry and cold air from the northern hemisphere, driven by radiative cooling, traveling in the lower troposphere. Considering the dynamic and thermodynamic effects of these monsoons, we divided the coastline assigned coordinate system into the negative and positive X channels. We hypothesized that the positive X channel that is far away from the equator has a higher potential for offshore propagation over greater distances. Our case simulation shown at the bottom captures these characteristics really well and assigns closely with GPM observations at the top. In the negative X channel on the left, convection on the second day propagate up to 300 kilometers offshore. And in the positive X channel on the right, it travels as far as 600 kilometers, an extremely long distance. This led to the next critical question: can density current directly drive organized convection to propagate such great distances offshore? Our answer is yes. Here we show two snapshots of the mixing ratio of water vapor near the surface from wharf, taken at 3 a.m. and 9 a.m. on the second day. First, let's focus on the right-hand side in the positive X channel, where the star indicates the regions of extremely long offshore propagation. Over these 6 hours, convection over the ocean generated a very mature cold pool here and with very perfectly circular shape at 9 a.m. We can also observe significant moist patches there where the air parcels have more thermal advantages to become new convective cells, thus helping push and organize convection far offshore. It's also interesting that the star on the left also show most patches that resemble the shape of coastline at night, especially at, for example, here 3 a.m. This suggests that the most patches can also occur at the front of land breezes. Thus, we propose that density current regulates most boundary layer thermodynamics and significantly contribute to convective offshore propagation. So what directly leads to exceptionally long distance offshore propagation in the positive X channel? Here the values represent the near surface horizontal wind speed projected onto the y-axis. The red colors indicate offshore winds like the land breeze, and the blue colors indicate onshore winds like the sea breeze. In the case study and in the positive X channel, we see a form of super long offshore propagation. So what enables this convective offshore propagation that goes far beyond the typical time limit of the diurnal cycle? By comparing two channels, we find that the sea breeze propagation is quite similar during the first day of the first diurnal cycle, but the key difference lies in offshore winds over the ocean during the second diurnal cycle. Even though cold pools are smaller scale features, The horizontal diagram after averaging along the x direction still reveals the gust front spreading over ocean and the leapfrogging process. This suggests that corpus generated on the first day can locally sustain the mesoscale convective systems over ocean, and under asymmetric background conditions, it continued to push convection offshore, contributing to long-lasting and long-distance propagation. And note that this corpus-driven super long-distance propagation does not occur every day. And next, we want to ask what environmental factors strongly affect the most patches and the most convection over ocean. One likely candidate is the sea surface temperature SST. So these two figures show the SST sensitivity of offshore winds in the negative X channel. In fact, the higher SST experiment on the right more closely resembles the climatology. The left panel is the control run, and the right panel is the higher SST experiment. During the daytime, the two runs look very similar. We see that the sea breeze colored in blue starting around 10 a.m. and moving inland, and then a sharp reversal once it meets the first mode pushed by the corpus there. The main difference appears after 10 p.m. and midnight, starting from the coastline and going offshore. The offshore wind speed increased very sharply once it crossed the coastline in both two runs. A uniform 0.k increase is far too small to directly boost the wind speed inside of the land breeze. This tells us that the strong SST sensitivity of land breeze largely comes from the corpus produced by the most convection, which is also very sensitive to SST. The land breeze front keeps triggering new most convection and the convection feedback onto the land breeze. Together, they allow the system to easily travel more than 200 kilometers offshore over warm ocean, and this process clearly depends on warm SST. So here are the key messages from this chapter that we first find land breeze is not just a local diurnal wind reversal like the sea breeze. It behaves like a density current, similar to corpus. Despite different cooling sources, both systems interact once formed. Most patches appear at both corpus fronts and land breeze fronts over the warm ocean, not just the formal. The late afternoon wind reversal inland is mainly driven by residual corpus, not the weakening of the sea breeze alone. And the corpus appears to play an important role in supporting super long distance that is usually more than 600 kilometers offshore propagation over warm ocean. The land breeze front detaches from the coast around midnight, marked by a sharp increase in offshore wind speed compared to inland flow. Its speed and duration sensitively strengthen with warmer SST. So right now we finish all the main conclusions and main results of this work. And next, I want to give some interesting topic about the discussion of this paper. So this study is a small work. This is a regional convection study. But as I worked through the result, I realized that many of these basic concepts are not exactly the same as what I learned from textbook, especially when they interact with each other. So in the discussion, I want to talk about this basic concept in pairs, their similarities, their differences, and how they interact. On the other hand, this work also highlights some physical process that seems new, and they may apply to offshore propagation in other regions as well. But I also want to point out some important preconditions, for example, warm SST. And also, we studied lines of convective cells rather than classic score lines, and a few others. So on this slide, I will compare sea breeze and land breeze and explain how they interact. So first, they have similarity. They are both commonly regarded as coastal density currents that propagate relatively to the coastline, driven by temperature contrast between land and sea. And also they have many differences. The sea breeze is moist and the land breeze is relatively drier. The sea breeze is deeper, but propagates slower. The land breeze is shallower, but propagates faster. So we suppose that the sea breeze is more like pulled by low pressure ahead, driven by radiative heating at daytime. And the land breeze is a kind of cooling driven typical density current. And also it may boost it by the cold pools. So also important conclusion here is that the depth does not predict the speed of various types of density current. And the sea breeze and land breezes in our case are both very long lasting. So they are not independent in space or time. This is how we call the sea breeze cold pool land breeze interference, especially the cold pools can build a connection between them. Here are 4 schematic diagrams of moist sponge layer dynamics to represent 4 different stages. Panel A shows the first one, the first stage. The daytime heating triggers convection over the ridge in the early afternoon. Then the convection, the first mode, moves fast from the steep terrain slope to the coast when the afternoon sea breeze here continues moving onshore. And panel B shows the first mode propagation meets a sea breeze front from the warm ocean, enhancing convection and leading to a robust cold pool. The sea breeze traps cold air in the boundary layer, contributing to the further jump. Cold pools help the sharp transition from long-lasting sea breeze to earlier initiated observed land breeze before sunset. Panel C shows the situation at night. The nocturnal land breeze driven by radiative cooling added by the residual cold pools to build what we call the hybrid land breeze, and also to generate new offshore convection as the second mode. The convection regenerated over the warm ocean, and this is also when the sea breeze cold pool land breeze interference finished. There is a distinct jump between these 2 modes, but these 2 modes can appear at the same time. And the most patches occur at the land breeze head, parallel to the coastline. And panel D shows a very special case that mainly talk about the nonlinear process, for example, caused by the cold pool interactions. And panel D is out of the typical diurnal cycle. The forward cloud over the ocean grows while the backward cloud over the land decays, and organized convection, the second mode, persists far offshore, from 200 to 600 kilometers, even after the sunset the next day. Continuing nonlinear cold pool interactions can extend the diurnal cycle itself and enhance and curve the moist patches, and enable the leapfrogging propagation at intervals of roughly 1 cold pool radius. And next, go back to my first question, land breeze and cold pools. So they also have very significant similarity that they both have negative buoyancy, even though driven by different sources of cooling. So because of the negative buoyancy, they have horizontal propagating speed. A little difference here is that a single cold pool is smaller in size and shorter lived. And also, of course, they have different thermal structure, so they will also have different propagating speed. Here we use the result from the simulation and use this classic budget method to estimate their horizontal propagating speed. The land breeze here has the estimated speed around 2.1 meter per second, and the cold pools here can propagate around 7.2 meter per second. In the result, our observed offshore wind speed is around 4.5 meter per second, just in between. So this is why we propose this hybrid land breeze hypothesis. The word hybrid here was inspired by my hybrid car. So you can see this means we have a mixing of elements and also mixing of dynamic and thermodynamic forcings. First, there is an elemental mixing of cold pools and classic land breeze. The 2 panels here shows the situation at midnight and also the early morning situation. And the red arrows represent the buoyancy-driven motions. We have the cold pools inside, And also we have the hybrid land breeze boundary showing in the blue curve. We also have mixing between the cold pool and the hybrid land breeze. So these two sources of cool dense air merge and reinforce each other once they form to form a deeper and stronger current. And second, we observe a dynamic and thermodynamic mixing that shapes the offshore evolution of this current, significant separated by the coastline. As the hybrid land breeze propagates over the warm ocean, it develops moist patches along its leading edge, features that resemble the most anomalies formerly found in cold pools. These moist patches arise from a combination of rain evaporation, enhanced surface fluxes, moisture fluxes, making the leading edge highly favorable for triggering new convection. This, in turn, generates new cold pools that feed back into and help maintain the land breeze current. And finally, in the left, a little tricky question or problem here is that there are two kinds of boundary. One is the cold pool, residual cold pool over land, and another is the radiative cooling-driven land breeze. Which front will cross the coastline first? And I think this one may have different situations in different islands. And one interesting factor is the reach to coast distance. In New Guinea, the large distance between the mountains and the coastline allows the cold pools to mature and merge with the radiatively driven land breeze before reaching the coast in most of the areas. But over many smaller islands in Maritime Continent, this reach to coast distance is much shorter. As a result, the cold pools may directly impact offshore propagation at earlier stage, even before the radiative developed land breeze forms. This is because the formal sea breeze cold pool interference can finish much earlier because of the shorter distances. And next, this is a very special comparison between the cross-equator monsoon and density current. It's a little special that we regard the monsoon system in our study as a kind of large-scale density current, because they really have some similarities. The monsoon here both arise from thermal contrast that produce air density differences with a clear thermal structure. And for the cross-equator monsoon here, we emphasize the three-force balance between the Coriolis force, pressure gradient forces, and also the friction. The Coriolis force should change the sign, change the direction when it crosses the equator because of the tropical beta plane. And another thing is the friction is very important in this force balance. The friction strongly influences the monsoon's direction and speed change. That means the monsoon should travel in the lower troposphere, and the dynamical core is around 1.5 kilometers. So that means the monsoon will not follow the quasi-geostrophic balance. It is a kind of large-scale density current propagating at lower troposphere and can directly cause the cross-scale interactions with other kind of density current. And of course, they have a lot of differences. The density current, including the cold pools and land breezes, are shallower and shorter lived. They propagate near the surface and very fast spreading. The cross-equator monsoon, they are deeper, the dynamical core is higher, and this is large-scale and steady. This is more strongly modified by Coriolis effect, and it is capable of altering SSTs and boundary layer instability. So here we add August for comparison. The right panels here shows the large-scale background conditions representing the cross-equator monsoons. The blue and red colors represent SSTs, and the wind streamlines represent the cross-equator monsoons. In February, the monsoon comes from the northern hemisphere and curve. In August, it's come from southern hemisphere and curve in a kind of similar shape. And when we go back to the Hammer diagram of this propagating convection, in February, they can propagate symmetrically at very long distance. But in August, when we look at it, the first mode of convection still propagates clearly in the direction perpendicular to the ridge, likely reflecting the robustness of the island's thermal-driven circulation. And the major difference here appears in the southwest part of the island. The second mode disappears entirely, together with the afternoon onshore weaker convection associated with the seabreeze front. And for the large-scale background state, the key seasonal difference is much lower SST, accompanied by faster near-surface wind that produce more evaporative cooling. So we conclude that the seasonal variation in the offshore propagating component of first mode is not pronounced. The second mode is very sensitive to seasonal monsoons at some places, possibly through SSTs and also the boundary layer instability. So this is the horizontal view of the cross-equator monsoon from a large-scale composite analysis, along with its suppressing influence on part of the convection. So how does this monsoon help support offshore propagation in our February case study? Our answer is mostly moisture convergence. In our earlier discussion, we emphasized the critical role of moist patches along density currents front. But as some of you may have noticed, in the case of very long distance offshore propagating cold pools, although there is a positive water vapor anomaly at the front, this is sometimes even weaker than the environmental field ahead of it. Now let's revisit, but this time together with latent heat fluxes and the role of monsoon. At the front of cold pools, the positive anomalies of latent heat fluxes is also quite evidence for the cold pools. The monsoonal head appears in the upper right of the figure, advancing towards the island with the monsoonal flow. And in front of it, there is a very pronounced increase of the surface moisture. Across this region, we see so many small cold pools with a little enhanced surface fluxes on the right. However, these areas does not show an obvious positive anomaly in latent heat fluxes. Why is that? What is the difference between moisture convergence brought by the monsoon and the moist patches generated by the cold pools? Before comparing these two concepts, let's review the monsoonal head from a vertical perspective and its cross-scale interaction. The monsoonal head is the head of colder and drier monsoonal flow. So firstly, the diurnal cycle of the island can affect the monsoonal head. The low pressure driven by radiative heating over land at daytime can not only pull the seabreeze front, but also the monsoonal head onshore. When the monsoon is too close, and especially when the air is very cold and dry, it can actually directly suppress the convective initiation of the first mode and its following offshore propagation. But when the monsoon is too far away from the island, its moisture convergence and its interaction with the second mode becomes weaker. So there is an optimal, moderate monsoonal distance and intensity that support both onset of convective initiation over land and the long-distance offshore propagation seen here. We can and add it back to the moist patches at the edge of density current. The moist patches are formed possibly from two ways. The first one is the entrained moisture fluxes from the surface because the density current propagate very close near the surface. And another way is the rain evaporation inside following the downdrafts. So, and also in our work, we find that the moist patches are also sensitive to a little higher SST over warm ocean. But the monsoon is different. The dynamical core is much higher, even though it's still in the lower troposphere. So this is large-scale, colder, drier, and denser air. And because of the higher dynamical core, it will entrain less surface latent heat fluxes to feed the moisture inside. And also there is no rain evaporation inside. So we gain the insight by comparing the anomalies of surface moisture and latent heat fluxes, which helps highlight the difference between these two concepts. The moist patches are located mostly inside of the density current, where the regions of moisture convergence lie outside of the cold air, often appearing ahead of the monsoonal head or accumulating beneath it. So we finally come to our conclusions, and first are the key messages that we study New Guinea Island, and we features two distinct modes. One is moving from the ridge towards the coast, another one is offshore propagating over the ocean, and they are separated by a clear jump. For the mechanisms, we mostly emphasize the multi-scale density current, including the land sea breezes, cold pools, and cross-equator monsoons. And they work together to modulate the most boundary layer dynamics to promote the long-distance offshore propagating convection. The zooming out conclusions also can be the two convective modes help connect the double peak of precipitation and clarify their distinct roles in a process-level understanding of offshore propagation. Besides of talking about different kind of density current, we want to have a better understanding of how multi-scale density currents interact and how they couple with most thermodynamics. And more emphasis in our work is placed on the nonlinear process that merge after convective initiation, for example, the cold pools. And then last, we study a very difficult but important phenomenon that is called cross-scale interactions, but we view this problem from a perspective of convective scale. So this is why we regard the cross-equator monsoon as a kind of large-scale density current in our work. So finally, thanks for listening, and especially I want to thank the ASP GVP program to fund this work, and also want to thank who offered me a lot of feedback during the Happy Hour seminar last summer also about this work. So thank you so much, and I appreciate any questions.
Okay, thank you. We have time for questions.
Thank you. Nice talk, especially graphics. I think you spend a lot of time preparing those nice pictures. Anyway, so this is, I'm assuming, typical for the MJO crossing the Maritime Continent when there is a lot of convection. Did you look at differences related to the MJO passage, or I'm assuming the convection over the island is always there because of strong topographic and daytime forcing, but the flow across the mountains may be different. And did you look at that?
Yes. So for this work, because I want to emphasize monsoons, so I only have some results also in February, and sometimes in February some MGO propagate through the Maritime Continent.
Yeah.
And I also think MGO is the biggest factor to affect this kind of offshore propagation. So MGO, the most significant difference is the moisture. So when the MGO propagate, especially the local active phase, the convective initiation is super strong. So the propagation are very symmetric. And at some phases, because before the MGO comes or after the MGO leaves, we have a little different background wind with easterlies or westerlies.
Yeah.
So that makes the propagation sometimes symmetric, but sometimes not very symmetric. But normally I feel like the general offshore propagation is very strong because of the moisture.
Hello. Okay, so I had a question. So something you mentioned was that even though the cold pools are small, they're still leading to unexpectedly more, I guess, convection and offshore propagation. Is that right? So I had a thought, and something I'm seeing in my current project, something I suspect, but I haven't done enough to prove it. But I believe that when you have all these circular cold pools, especially because they're circular, different than a sea breeze, especially if many of them, they collide with each other. And so that collision causes moisture convergence, not even just at the edge, but it could be in the region. I guess it's more moist and because cold pools are cool and dry, but in this region in between the colliding cold pools, it might be moist and warm because of the SST. So I was wondering if you had any thoughts on that.
Yeah, this is a very important and very interesting question. So in the paper, I talk more details about those cold pools. I think in this situation, we can separate the cold pools into 3 different regimes. The first one is the one I talk the most about, the residual cold pools over land. So this is more familiar. And I think what is more related to what I talk about is the embedded cold pools. So why I call the embedded cold pools is because the front is moving, and the front generated convection is also moving with the front. So that makes the cold pools very hard to develop locally. The cold pools are moving too, and also once it generated, it quickly merge with the front of sea breeze or land breeze. So in this work, I call that the embedded cold pools. We can find them in both the sea breeze front and also the land breeze front. So I think so. I think the most patches here at the edge of land breezes also may due to some embedded cold pools inside. A little hard to prove it, but maybe we can use what we normally use, more than 10 million Lagrangian particles, to prove that later on. Yeah.
Thanks. Thank you.
I also want to say nice graphics. I enjoy those. Did you draw those, or did AI draw those?
I drew this.
You drew those?
Yeah.
Wow, awesome. It's really great. My question was, what would happen if New Guinea was completely flat? Would it be fundamentally different, or would it be just slightly different?
Yeah.
With the 2 modes?
Yeah, unfortunately, I have another work totally with flat island in the idealized work. And to compare with this, I would say that most of the phenomena are very similar in our flat island. And of course, I think the ridge can cause some different. So firstly, the mountain ridge over tropical island, they're caused by volcanic evaporation, and they almost look like a straight line. So I think this is caused the convective initiation over those tropical islands almost start with a straight line. So I think this is interesting. And also because of the slope. So when we first have cold pools, the density current, when the density current propagates over a very sharp slope, the propagating speed is of course much faster than over a flat platform. So I think that caused the initial propagating speed faster because of the ridge.
Thank you.
I have a question about the moist patches. So you did a sensitivity test with latent cooling from evaporation of rain turned off, I think you had said in the WRF simulations. And I'm assuming then the offshore propagation probably dies, or it's not as strong. But with the warm patches, I'm wondering, they definitely, you see them, they occur with this, but how important are they? Are they really necessary for the long lived propagation offshore? Like if you had a way to remove them, would it have much impact on that? Or is it really more cold pool driven?
I think this is a very important question, but I cannot answer that with the current experiment. So the sensitive experiment about the tropical cold pools, I think, is still the challenge right now. And for me, I tried a lot of different methods, especially for another work. But I would say I still cannot find a perfect way to show the result. Because after, for example, after we turn off the evaporate cooling, a lot of things are changed. So I don't know how to prove the moist patches, like you said, how important they are. Maybe some kind of sensitivity experiment, or I think the more actionable is to track with more than 10 millions of Lagrangian particles. But it's very hard to do that in WRF. Yeah, so yeah, I don't know whether I answered your question. Yeah.
Yeah, thanks. Any other questions? Oh, Rosie has a question. All right.
Hi, very nice talk and very nice graphics too. Very impressive that you made them. You talked about many scales, and I'm wondering if you have also thought about even smaller scales like mountain and valley breezes. So like when you have terrain like that, the slopes heat up at a different rate during the day and causes this mountain breeze. So I'm curious if you have thought about that as well. How could that come into your hybrid picture?
Yeah, I think in this work, I tried to do some analysis first, but later on, I feel a little tricky thing here is because, for example, I emphasized the katabatic winds in the introduction, like the valley breeze, but in fact, the first mode propagate in the afternoon, so this is before sunset. So it's a little hard to say whether the ridge could contribute the first mode propagation. But I think, yes, for the hybrid land breeze, it may contribute that at midnight, the radiative cooling may strengthen, over the mountain may strengthen this kind of hybrid land breeze. So yeah, this is the...
Okay, thank you. And another question, so the storms form primarily through orographic lifting? Is that how they get initiated? The first mode?
So firstly, even with the totally flat island, this kind of convective initiation also happens because the sea breeze. So even totally without the topography. And I think, of course, the ridge, especially this very high mountain, this is 4 kilometers high. And I think orographic lifting is very important for the convective initiation. In a former work by Professor Yuqing Wang in 2008, and they did a lot of sensitive experiment about topography and to show that the convective initiation in New Guinea is very sensitive to first topography and second the cross-equator monsoon. But in my work, I mostly focus on the process after convective initiation, that I suppose the initiation is the same. Yeah.
Okay. Thank you.
Perfect. Okay, if there's no more questions, let's thank Mingyue one more time.
Hello.